Hello everyone. We are going to solve the September 2022 NET questions for the chemistry, and I will be doing only the organic questions, and in this video I will be doing the first 5 organic question. So the question was, guess the product, predict the product formed in the following reaction. So this is the first molecule, and the first step you can see it reacts with acetic anhydride in presence of BF3 dietherate. So BF3 is a Lewis acid. It will activate this acetic anhydride, and acetic anhydride will of course act as a electrophile. So we can understand first step will be electrophilic substitution reaction, and then next they are reacting with CnCOOET. So what you have to understand is this molecule is a heteroaromatic molecule. To understand this, when you have a heteroaromatic molecule, this molecule we are taking one part of it, that is the pyrrole part of it. So the substitution can occur at this alpha position 2, or it can happen at beta position number 3. But we will always see that major product, mostly the electrophilic substitution reaction occur 2 and not 3. Why? Because at position 2, that is alpha position, this is kinetically favored. The intermediate, rather the transition state which is formed when substitution occurs at position 2, it is much more stable than when the substitution occurred at position 3. So see what happens when attack occurs at position number 2. So of course nitrogen takes part in the uh, ring activation. This donates electron, this comes here and takes it donates electron to electrophile, and you get a positive charge on nitrogen. Then this pi bond is stabilizing this positive charge, and you get positive charge here. Then again this pi bond is involved in stabilizing the positive charge. So what is happening is both this pi bond and this pi bond, rather we can say both this pi bond and this pi bond are involved in stabilization of this positive charge. So when it is when two pi bonds are stabilizing, the positive charge is delocalized over long range. You can see here it is delocalized over here, then here, and then here. So it is reduced and therefore quite stable compared to when attack occurs at position 3. So imagine when this pumps here, you get here, you get positive charge on this nitrogen, right? Same. And then when it pumps, you get positive charge again. So again it's basically only one pi bond is there which is stabilizing the positive charge. You can see very clearly, see that the positive charge is delocalized between this nitrogen and this carbon atom. So it's not much delocalized, quite localized, and therefore it is not very stable, and therefore the intermediate is less stable, and therefore it is tough, and the activation energy will much higher, and therefore electrophilic substitution reaction occurs at position number 3. So for this molecule, anyway everything was blocked. I talked all that so that you know that electrophilic substitution reaction occurs at position 2, and then you are reacting it with first with BF3. So BF3 is a Lewis acid. Its octet is not complete. BF3 has one vacant p orbital. So this oxygen of the acetic anhydride, it goes and donates electron, and you get this species, and this goes and attacks here, this comes here very clearly, then once it comes back, once this comes back, this goes out, and you get electrophilic substitution reaction at alpha position. Then again it wants to become aromatic, so this H will be taken away by this acetate, this goes back here, this comes here, and you get back this aromatic heteroaromatic system. Now what happens is you are still having BF3, and next to it is there is COH, and the CH3 is next to the C double bond O, so this proton is to a certain extent acidic, so it can undergo ketonol tautomerization in presence of acid or base. Now BF3 is a Lewis acid, it can undergo tautomerization, and then transesterification can not transesterification, esterification reaction can occur. So what happens is, because BF3 is present, this undergoes ketonol tautomerization. I should have drawn something like that. So CH2 is here, and there is a hydrogen here. So this donates electrons here, and this comes up, and this picks up proton, and therefore you get a double bond here CH2, and this becomes OH. Now this OH and this COH can undergo Friedel-Crafts can undergo esterification reaction. So again lone pair on the ketone, this goes and pumps to the BF3, Now oxygen gets positive charge, it becomes much more electronegative, and therefore it pulls away most of the electrons from here pi cloud towards itself, and this becomes highly electron poor center. So this goes and attacks here, you get here, then this picks up proton, you get OBF3 minus, this comes away, this goes away, and you get this species. Now in the product, none of the product showed this. So what else can happen? Of course it will not stay as double bond CH2, right? This is not stable, this is kind of enol, because en is there, O is there, so it will try to become single CH3. So what happens? So this water takes away this proton, this comes here, takes back, and then you get CH3, right? Now what happens? Now it is not an aromatic system, it's a diene, and in the next step you are reacting with CnCOOET. Now CnCOOET has this C double bond and C triple bond, and so this can act as a dienophile and this can act as a diene. So you know, diene and dienophile, they undergo what is called as Diels-Alder reaction. So this will react with your alkene and will undergo Diels-Alder kind of reaction, right? So pericyclic reaction, cycloaddition reaction. Okay. So what happens here is, now you are having this 4n system and you are having this 2n system. This is diene, this is dienophile. Diene because 2 alkene and diene. Dienophile means one who loves diene. So now what happens is, this is what we have to understand, the regioselectivity. This goes and attacks here, this comes and attacks here, and you are getting this product, and this bridged CO2 will be easily lost, and you get something like that, and you get this product. Now the question can be, why this goes and attacks here? Why not this one goes and attacks here and this comes and attack here? Why this kind of regioselectivity is seen, right? So that's very simple to understand. Basically, diene generally acts as nucleophile and this generally acts as electrophile. So that means they donate electron. Nucleophile means Nu minus, it pumps electron, it gets attracted towards uh, positive polarity, and this acts as electrophile, so it is E plus, it accepts electrons from nucleophile. So if you see here, between this and this, which one has more negative charge? Between this carbon and this carbon, which one has more negative charge? So this is next to nitrogen, nitrogen donates electrons, so it gets negative charge. So clearly this is where more negative polarity is there, so the first attack occurs from this on the electrophile. This determines the regioselectivity from the diene part. Dienophile, what happens? Dienophile has to accept electron. So if this comes here, you know, this pi bond can be delocalized between this and this, and you get positive polarity on the nitrogen, right? So because of that, the attack happens from this carbon to this nitrogen, and this goes here, and that's what you get the regioselectivity. So yeah, we know this HOMO of diene interacts with the LUMO of dienophile. That's why diene acts as a nucleophile, and LUMO is lowest unoccupied molecular orbital. Unoccupied, that's why it can accept electron. HOMO means highest occupied. So nucleophile means that orbital attacks which has maximum energy, so that is HOMO, and therefore diene acts as nucleophile, dienophile acts as a electrophile, and this reaction occurs, right? The answer is option number C. You can check it back. I'll go slowly, you can read through it, whatever I written slowly. You can pause it if you are having like you are not able to read. Moving on to the next question. The next question says the correct statement about the following reaction is. So you are having this molecule where you are having ketonic group and hydroxyl group is there, and you're reacting with Me4N. So Me4N plus will be there. It's a kind of ammonium salt, tetramethyl ammonium salt, and you are having this part as minus BH minus OAC thrice, uh, and you are using this as solvent CH3CN2 nitrile and then ACOH, and ACOH of course is acetic acid, right? So the question says the correct statement about the following reaction is it involves intermolecular hydride transfer and the product is achiral, or it involves intramolecular hydride transfer and product is achiral, or involves intermolecular hydride transfer and product is chiral, involves intramolecular hydride transfer and product is chiral. So that means we clearly need to draw the mechanism so that we know that hydride transfer happens intermolecular or intramolecular, and then we have to find out the product so that we know that it is chiral or achiral. So now this molecule is like far relative of your NaBH4. So NaBH4, you know, Na plus is there, BH4 minus is there. So this part is kind of BH4 minus, um, Na plus BH4 minus. BH4 minus, this will be less reactive, and what happens is because boron is having negative charge here, see what happens is something like this is there. Boron is there, it has hydrogen, it has negative charge, it has 3 OAC groups. Now because of this negative charge, all the bonds from boron are nucleophilic in nature, and therefore this BH bond breaks and it goes and donates electrons. It's a hydride donor, right? So uh, yeah, that's what happens. So initially the first step will be this OAC minus itself leaves and this acts as a Lewis acid, right? So this leaves and then this OH goes and donates electron and you get this. This is important. It gives you the stereo selectivity. It will direct from where the hydride donor occurs. Now once this attacks, again boron gets negative charge, and as I said, because boron is having negative charge, all the bonds from boron are nucleophilic in nature, and therefore this goes and attacks. So please understand, this OH was towards the viewer, so of course this boron is also towards the viewer, and this BH bond attacks from front, and this oxygen is pushed behind and picks up proton. Therefore you are having hydrogen in front and OH behind, and here's of course OH is front, and you are getting something like this. Now how do we know it is chiral or achiral? So if it has plane of symmetry, it will be achiral. If it does not have plane of symmetry, it will not be achiral. So you can see very clearly here, actually, if you imagine this screen as a plane. So what happens, you see behind the screen is OH, here front of the screen is OH. So of course it is not chiral, but best way will be to convert into Fisher projection formula, and then you will get easily. So you see here, we have drawn it like that. So I just catch this CS3 and put it front on the top. So this CS3 goes here and rotate it something like 90 degrees, so that CS3 goes away from the viewer, and this H and OH, they both come towards the viewer, something like that. Okay, so what I have done is I have lifted this molecule so that it becomes straight. So once it becomes straight, it would have been something like this. Okay, this is your CH3, and you are having H front, H towards the viewer, and OH away from the viewer. Okay, then what you do is you rotate 90 degrees, so that CH3 goes behind, and then what happens is H is coming front, towards front, but it comes towards this side, right side, and OH goes again comes front but towards the left side. Similarly the same thing will happen here. You're getting this, you know, Fisher projection formula is basically the vertical line is away from the viewer. So this ME This ME is basically away from the viewer, so this CSC we are putting in vertical line. Similarly, this ET was also away from the viewer. I should have drawn that, I missed. And then OH and H are sorry, away from the viewer, and this OH and H, they are towards the viewer. Similarly, this OH and H are towards the viewer, so they come in the horizontal line. So you can make this H in the horizontal line. This is towards the right, so you are having OH on the right, sorry, H on the right, and this OH is on the left, so this OH is also on the left, and this OH is on the right, so OH. Then you can see this is the plane of symmetry at all if you want to imagine, but they are not sitting on each other. There is absolutely no plane of symmetry, so it will be chiral. So now, as you can see in the question, the hydride transfer happened intramolecularly. It happened within the molecule. Though initially it looked like this far relative of NaBH4, it will donate hydride. But first what happens is it acts as electrophile. This goes and attacks, and then intramolecularly hydride transfer occurs. So the answer will be intramolecular hydride transfer, and the product is chiral. So this D is the answer. Okay, involves intramolecular hydride transfer, and the product is chiral. Right. Next question, the reaction which will furnish tertiary butyl C double bond OPH. So it's a ketone, okay, and as the major product are. So they given this reaction, all of them looks like they will give, but this was interesting question, and the one which looked most is not the right answer. So you know, tertiary butyl COPH is basically this, okay. The common name for this is pivanyl chloride. Oh sorry, not pivanyl chloride. Pivanyl chloride is this one, right? So what happens is, let us look at the reaction. So of course this looks like Friedel-Crafts acylation reaction, where you are having benzene and then acyl halide in presence of Lewis acid. But the problem is this pivanyl chloride, this reacts with AlCl3 and then immediately breaks up to give you tertiary butyl carbocation, because a tertiary carbocation very stable. So that's what happens first. So this chlorine donates electron to aluminum, chlorine gets positive, aluminum gets negative, and then oxygen donates electrons here, this gets out, and you are having AlCl4 minus, okay, and you are getting this. Then this gets out as carbon monoxide, and you are getting a positive charge. So that's what is important. And then of course when this reacts with benzene, you are getting this product and not the required benzene C double bond O tertiary butyl, right? So this is not the answer. Second is very simple. You can look here, you are having benzene C double bond O CH2 CH3. So of course this hydrogen is to a certain extent acidic, because if you remove this proton, how do you know any proton is acidic? After removing that proton, the product form should be stable, the anion form should be stable. So here the same thing happens. So once you remove this proton, you get a negative charge. That negative charge is delocalized here, and you get negative charge on this oxygen, right? You get negative charge on this oxygen, so it's quite stable. So this comes here, then this attacks here, this leaves, and you are getting this species. So again, sodium hydride is a very powerful base, because it is Na plus and H minus, Na plus and H minus. Now H minus is very small in size, so lot of concentrated negative charge. It's a very poor nucleophile, but very strong base. It goes and attacks this proton. So similarly it goes and again attack this will happen again, and you're getting the requisite. So B gives the product, expected product. C, see what it says. You had benzene on that CN was there, so cyanobenzene, which reacts with this Grignard reagent, this tertiary butyl MgCl. So we know that magnesium has positive polarity and carbon has negative polarity, because carbon carbon is more electronegative than magnesium, or rather you can say magnesium is more electropositive than carbon, so it donates the electron. Other way to look will be magnesium is there and carbon is there. Carbon is much more electronegative than magnesium. So of course, so when both of them interact, both the atomic orbital interact, they will give you two molecular orbitals, right? So electrons are happier with carbon than magnesium because carbon is more electronegative, so it has lower energy. Electrons are more stable here, so it has lower energy than magnesium, and so then in the molecular orbital picture you are having electrons, the bonding molecular orbital closer towards carbon and anti-bonding molecular orbital closer towards your magnesium, and therefore carbon is nucleophilic, magnesium is electrophilic. So carbon is nucleophilic, that means it donates electron. So this carbon goes and donates electron here, you get this, and you just hydrolyze it, you get back your carbonyl, and therefore this also gives the product. Now in option D is pretty much same. So you are having organolithium. Again, lithium is metal, so it donates electron to the carbon. Carbon has negative charge polarity, this one has positive polarity, so the negative goes and attacks here. This will go up, this will come down, and Cl minus will leave, and you get your product. So B, C and D, those three options would give the product that was coming as option number B. Now question number 4, the correct sequence of reagents to affect the following transformation. Now you are having this naphthalene molecule, on this you are adding bridge. So what you are basically doing is you are breaking both sigma bond and pi bond. So it says among them which is the correct one. So you are having A, B, C and D. So first one you can see you are adding chloroform and NaOH. So Riemann-Tiemann kind of reaction you would have seen in Riemann-Tiemann reaction. If you don't remember, please Google right away, get this reaction. So first step will be formation of dichlorocarbene, right? B is DDQ. Now DDQ is a oxidizing agent, basically dehydrogenates and oxidizes molecule. It is generally used for aromatization of molecule which has capability of becoming aromatic. And third one is third and fourth, both of them, first step if you see, it is basically Birch reduction, right? So when you do the Birch reduction, they will give you Decalin system, and then it will be easy for it to reaction to occur. Okay, so option A, what it says is it's highly unlikely, because on aromatic ring, if you do take this chloroform and NOH, what you are getting is CHCl2, right? Sorry, CCl2, you get dichlorocarbene, CCl2, which is an electrophile. So now if electrophile is there, of course attack can occur on alpha or beta position, mostly it happens on alpha because this is not such a bulky group. So you will get alpha here, CCl2, and then you can't make out then how then this reaction will occur. B to surely not, because it's a completely or stable molecule, this cannot oxidize it. Oxidizes by dehydrogenating, there is no way you can remove any proton. So of course answer has to be from option C or D, so that Birch reduction occurs. So when you do Birch reduction, this is what is formed, you get this Decalin system. Okay, now this Decalin system, what happens is, if you see this pi bond and this pi bond and this pi bond, this pi bond has only 2 electron donating groups, right? This also has only 2 electron donating groups, but on this pi bond you are having 4 electron donating groups by hyperconjugation. So these are all electron donating groups, 4 alkyl groups are there. So this is the most reactive alkene in this molecule. These are the most reactive alkene in this molecule, and therefore electrophilic addition, it's not substitution, addition reaction occurs in the middle one. So first CCl2 octet is not complete, you can see 2 electrons on chlorine, 2 electrons chlorine, and one of the p orbital has lone pair, another p orbital is vacant. So this goes and attacks on this, and this goes and attacks here, and you are getting this species. Then what happens, again you are adding, yeah, where the thing, Okay, CHCl3NOH is there. So what happens is further this same molecule, the same Birch reduction condition will help to remove this CCl bond, because they are reducing agents. They will reduce this CCl and put two hydrogens here. The last step is DDQ. So DDQ, what it does is basically DDQ oxidizing agent. Oxidize so that you get aromatization. So DDQ is, this is the molecule DDQ. Okay. So dicyanoquinone molecule. So first thing is, this is very interesting. This carbon carbon sigma bond breaks here. This H is picked up by this, and this comes here. You get OH here, O minus here. This picks up proton, it comes here, and you are getting this. So the answer is option number D. Right? What was option D? You are having Birch adduction followed by chloroform methanol, and then again Birch adduction, which we saw for removing that CCl, and then DDQ, right? So this Birch adduction first made it into Decalin system, and then this gave dichlorocarbene, so that the electrophilic substitution reaction occurs in the middle, and then again Birch adduction to remove 2 CCl, and then DDQ to aromatize it. I'll go slowly. Please go through this. Okay. Please read it. Pause it if it goes little faster. Right, the last question. The last question says the stereochemistry of the double bond in the product is. So it says this is the reactant, and you are having 3 double bonds at the end. It is asking what is the stereochemistry, EZZ or EZZ, whatever it is, EEZ, and 3E5E7Z. So we have to give the naming also. So a very simple reaction. In heat condition it is sigma tropic shift 1,7 sigma tropic shift 1,7, 7 plus 1, 8 electrons are involved, so it is 4n system. So 4n system should generally happen by photochemical reaction, but 1,7 can occur both in photochemical and thermal condition, because it's a very long bond, and so they can rotate and reach each other. So in photochemical condition it will occur suprafacially, but in thermal condition, what is given here, the attack will occur intrafacially, which is not needed here, but I was just revising for your sake. So what happens is, you are having this molecule. So how do we give the number? This bond is broken. So whenever you are breaking the bond, put both side the same number 1 1, then 2 3 4 5 6 7. This breaks here, this comes here, this comes here, this comes here, and so where the new bond is formed, you have to give that number. So when the new bond is formed between this 7 and this 1, so it is called as 1,7 sigma tropic shift. See the number of electrons involved. So this is 1 pi bond 2 electrons, another pi 2 electrons, plus another pi 2 electrons, 2 plus 2 plus 2 is 6, plus this sigma bond, so it is 8 electron system. So it was 4n system. Okay. So this goes through this transition state. This hydrogen is being shifted here, this pi bond comes here, this pi bond comes here, this comes here. Okay. Now we are least bothered actually that attack occurs by intrafacial or superfacial, because this the hydrogen is being added on this carbon, it is getting 2 hydrogen. So it is not at all chiral. If it was chiral, then it makes a lot of difference that hydrogen is coming from front or away from the viewer. So here that does not matter. The thing is this system was already conjugated. So this single bond is not freely rotatable, because this pi bond and this pi bond was in conjugation, this pi bond, this pi bond. So the rigidity was maintained and is seen at the end of the product also. So When this hydride comes here, this moves here, this moves here, this moves here, and so what you're getting is this pi bond, this pi bond, this pi bond, you're getting this product, right? And so you can see here, we have to give the counting now, because 3, 4 and all. So COM is the most oxidized state, so of course if you give IUPAC number, this gets first preference, this gets second, third, fourth, 5, 6, 7 and 8, right? So now what happens is, um, you see between 3 and 4, this has carbon and this is hydrogen. Here it is carbon, this is hydrogen. So we have to give uh, what is that called as, we have to give absolute configuration for the alkene based on the CIP rule, right? So you can see here carbon and hydrogen, we have to go step by step for each atom. So between carbon and hydrogen, of course carbon gets more preference than your hydrogen. Here also this carbon gets more preference than the hydrogen. So this gets first preference, I have written small this 1, and here also this gets 1, and this hydrogen get 2. So because the substituents of same priority are on the same side, this at position 3 I'll call it Z. Z means together, E means across, right? Similarly, if you look here at position 5 and 6, hydrogen, there cannot be anything which has lower atomic number than hydrogen. So of course you can see the two hydrogens are on same side, so again it is Z. Whereas here on the 7, 8 you can see the two hydrogens are apart from each other, right? The lower bulky group, the lower priority groups, they are away from each other, and carbon gets first priority, this carbon gets first priority. Again you can see they are towards the they are on the opposite side, so they will be E. E means across. So the absolute configuration is 3Z, 5Z, 7E. Answer is option D. So whatever I written, I'll go very slowly, you can read through it. Okay, that's it for the today's lecture. Thank you so very much.